he visited quite a few times, I guess. And I don't know, probably the students, remember some of the faces of the students?
No,
probably not.
Because they have graduated, I think.
Yeah, right. That's the pandemic, I think. We got a long absorbing science state, right? Okay, so he did his graduation from ISI Kolkata. Then he moved to Cornell for his PhD. Came back to ISI, I mean assistant professor. So then he went to ISI Bangalore, where he presently is at the level of professor. So today he will talk about this is the title, right? How to tell a tale of two tales.
I've changed it too.
Okay,
So that I can use this picture.
so Parthanil,
Yeah. Okay. Thank you for the introduction. So, two things. All of you know this picture, right? Anybody doesn't know, I can explain what it is, but it's just. Although I'm just using it for the two tails, I'm not going to talk about two tails. I'll only talk about one tail. Just to show this picture, I've kept this time. Secondly, you should be very careful. Last time I visited, he was talking about it. That was a historical day. The day I visited, that was the day of demonetization. So I remember it very well because I got some honorarium in 500 rupee notes, and then later on I had to use it up somehow in the bank and so on. Sorry, it was not just. So you have to be careful today, okay? Something more interesting may happen. Okay, so anyway, so oh no, anyway, so this is a talk that is actually joint work with many people. All of them are written. The names are written here. Main two collaborators are Rajot, who also came on the same day and gave another talk, very nice talk. And Oyon is my student, who is now a faculty member of IIT Bombay Math Department. And then there are various people, like this is my colleague, and this is a this was a master student of ours, very smart. He went to, he's now in Stanford, and then he's in France, etc. So he's in Poland, as the name suggests. Okay, so what is this about? So this talk is about a model called. Since there is recording, is there? If there is anyone who's on the online audience, please request them to just unmute and ask the question. That's best. I don't mind disturb. I mean, it's not disturbance. If they already asked, that's better. All of you, please feel free to ask.
Are you using the microphone?
I'm not. Should I use it?
For the online.
Okay. 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 I'll use it. Especially recording purpose, I guess this is better. So, right. Oh, sorry. Now I have to tone my voice down. Oh, so this talk is about this model called branching random walks. I'll explain what that means very soon. And then there are two tales that I'm going to talk about, and these tales are what are called the progeny and displacement random variables. I'm going to tell you also what that is. And the key question is, how do these tales affect the branching random? It's a very vague question, but I'll tell you what that is. And we'll try to answer this question in a very, very special case. I believe in giving talks in a special case so that people can get the gist of the method. And then, of course, the generalization I can tell in the end. Okay. So, what is the branching random walk? So, the branching random walk is, roughly speaking, is just broad description. It's a growing collection of particles, or you can even think organisms, which starts from a single particle or a single organism. And then they branch. When I say branch, I mean split. So a particle is splitting into two particles. And they spread independently of their positions and of other particles. So basically the particles behave independently of each other, and then they spread. I'm going to make it more precise. So this is the model. Now we are going to consider a toy model where there is no interaction between particles. In the sense, two particles, the way I will assume it, these two particles can even cross each other without even colliding. You can think of it like they have a very thin strip. Okay, I know. I'm just going to say it. Thank you. There is a very thin strip where the particles are sort of moving without colliding. So if you want to introduce collation, etc., then it will be more complicated. It's beyond our scope at this point. Okay, so this is what we are going to assume. And the question is, the broad question is, what is the long run configuration of the positions of the particle? Again, this is a very vague question. What I exactly mean by that, I'll try to make that precise. Now, this model, if you go back to history, it was actually introduced by Biggins in 1976. But if you look at Biggins' paper, it clearly depends very much on the paper of Hammersley and Kingman in the 2 years and 1 year before that. And therefore, whenever in any branching random walk talk or in work, whenever they give reference, they always mention all the three names, H, K, and B. What is the dynamics? So you start with a single particle. So here time is going to be discrete. So think of things happening in say first minute, second minute, and so on. Of course, there are continuous time models as well. That will make things more complicated. We are just going to do things simple. Start with one particle. Now what happens is, at time 1, this particle splits into a random number of particles following some distribution. Say first it branches into 3 particles. And all of these 3 particles will make a displacement. And the displacement is also going to be random. But the displacement is not, they are not going to depend on each other. So if this one goes right, not that the other one will come left, etc. It's very unphysical in the sense that if you think of, say, preservation of quantum mechanics, momentum, etc., it's not happening. So, but there are other models where you can introduce dependence. I'll talk about them later. At this point, I want to consider the simplest possible model where the particle is splitting and making independent displacements. If you don't like particles, you can think of them as a colony of bacteria or something. Okay, then each displacement is random and they follow some distribution for displacement distribution. There are 2 distributions involved here. One is progeny distribution, which tells you how many particles will be born from one particle. Okay? And another distribution tells you how far they will go from the position of their parent. Then this will go on. At time 2, each particle here will split and move in a similar fashion as this one, first one, independently of each other. Now it can so happen, this is not there in this picture yet, that some particle just dies off.
Does progeny include 0 as well?
Yes, exactly. That was what I was going to say. Some particle may die off, so progeny may include 0 as well. So you might see that here there is no such particle yet, but I think the next generation you will see it, that some particle is not going to have any children allowed. Oh, so here I think, yeah, this one has no progeny. There is no next generation. And particles can cross each other. By the way, this is just a description. You are actually not seeing the entire thing. You are always seeing the snapshot. You are not seeing the entire genealogy. Say at time 3, you are only going to see this snapshot. Okay? You don't know which one has a common parent, which one has a common grandparent, etc. The genealogy is not given. You just see this. And then we have to conclude various things from this picture, just this snapshot. Anyway, so let's go back to this picture. As you can see, if you go back here, the description here, if you actually knew the entire genealogy, description does look like a tree. In a graph theory, this is called a tree. Right? So this looks like this. So you have time 0, and then you have time 1, time 2, etc. What we are going to do, we are going to always think of displacement of a particle would mean that the parent was here, projected here, so the parent position was here, the child moved this much, so this is the displacement of the particle from the parent. On the other hand, when I say position of the particle, I mean this is the displacement from the parent position. When I say position of the particle, I mean how far it went from the origin. So the one particle, the first 0th time point, 0th generation. By the way, the word time and generation are used interchangeably because time is discrete. So 0, this was at origin in the real line. So with respect to the position of the first particle or the particle at time 0, how far this particle has moved. That's the position. And that, of course, you can see the position can be found by total displacement from the origin. So you have to find the displacement of all of its ancestors, honoring the sign. This is moving also negative, right? So you have to first then add this much, and then here they have subtract this much to get this. So is it clear the difference between position and displacement? So displacement is how far a particle is moving from the position of the parent particle. Absolute position is just how far the particle is from the origin. This is the model. Of course, I haven't told you what is the progeny distribution that I am trying to take, and I've not told you also the displacement distribution, etc. I'll come back to that. But before that, let me tell you why this is important. So this is important because they appear in many contexts, especially statistical physics, and also I have seen that they are also used in biomathematics. Let's say biologists also use it because instead of particle, they will think of an organism. But I don't know much about that. But statistical physicists are really excited about branching random walk. That you will see that in the talk as well. So it can be used to describe how a growing population of say particles or a bacteria, say, they invade a new environment. That's the motivation. And we'll talk about in particular power law displacements. And the motivation from that for that would be, I think, ecology, but I'm not an expert again. There's something called Levy flights, where you have power law displacements. Okay. So in our simplified model, as I said, we are going to. Okay. So now I'm going to make an assumption. So earlier, I was telling you that the displacements can be both positive and negative. I'm just going to make my life simpler and simpler as we go along. So the next assumption I'm going to make is that the displacements are going to be strictly positive. So in particular, you have this origin. Everything is going towards this ray. This origin to on the right side. So everything is happening. The entire dynamics is going to happen on the positive side of real life. It's not necessary at all to have that like that, but I'm just doing it for the sake of simplicity. Okay. More complicated models will arise where particles can move in a plane, on a table, or on a box, in a box, etc. Again, as I said, for the purpose of this talk, we'll restrict ourselves to a very simple model, and then we'll study what is called the long-run configurations of the positions of the particles. I'd used this phrase before, long-run configuration. I'll try to at least explain to you what I mean by that after a while. But quickly, some connections. Here are some connections of two models in probability theory or statistical physics. These are all various papers. This Roy is Rishi Roy, not me, someone else. And all of these, by the way, all these connections and various other connections to biology, etc., can be obtained from notes of Zamshi. So if you just Google Zamshi plus branching random walk notes, you're just going to find it. Much easier to do. Remember it this way. Okay, so any question or comment or concern before we move a little bit into technicality? So far, I haven't really said much. Yes.
Position displacement distribution.
Yes.
Displacement will be on a lattice or
At this point, it's on the real line.
on the real.
Yeah. But you can also do lattice, etc. Those models are.
Any qualitative difference, like not the difference.
Yeah, one qualitative difference, as you said, is here I'm going to assume that the displacement distribution is continuous. So no two particles will be at the same position.
Right.
But if you assume it on a lattice, say one dimensional Z, say, then only integers, then of course there will be basically discrete and there will be particles in the same point, etc. Then there are some other dynamics can occur. Here I'm just going to assume things are continuous. So that's a good question. But there are models, I must tell you, where they allow things only on the lattice. And then whenever two particles come together, they either do what is called annihilation, like they just destroy each other, or they coalesce, they become one particle. Sometimes you have models where with probability P, coalition happens, or with 1 minus P, annihilation happens, and people analyze that. But so that's a very different model altogether, and I think it's much harder to analyze. Many of the things that we use will fail. Yeah, thank you. Anything else?
Yes. So is crossing allowed where
Yes, that's what I said. Crossing is allowed.
when branching is taking place?
Yes, in the sense, yes. In the sense, say you have two particles here and here, and then this 4 becomes 2 and 2, they cross. If you look at this first picture,
Yeah.
I'll come back to you. Yeah. So first picture there that was there in the third generation, I think. Yeah. Here is crossing. So you can think of that particles are moving in a very thin strip so that they can avoid it.
But when
So in terms of the scale, particles are too small compared to the strip.
So you are considering so is the distinguishing the particles is
Sorry.
distinguishing the particles is present. You are assuming that. You are able to trying to track them, right?
Yes.
So
yes.
for example,
Yes.
the
The particles are distinguishable. Yes.
right.
We are in a fermion. We have to have that.
Yeah. So, no, you shouldn't have that.
Yes.
Shouldn't have.
Oh, you shouldn't have that.
Yeah, fundamental particles all will come.
Oh, okay. No, but that boson, isn't it? I should always keep forgetting.
Boson are identical particles.
Identical. Okay.
Yeah.
Sorry, sir. The joke didn't make sense.
No, what I'm saying is that equal to 2
Yes.
equal to 3.
Right.
Suppose take the first two particles.
Yes.
The first two from the
First,
left.
this
From the left.
left.
Yes. So I could have interpreted these two.
This is
not
going
cross-
there and
yeah,
that going
not
there.
crossing, but rather.
Right.
Yeah,
Yeah,
how
it's
do you
true.
remove
What
that
you are
ambiguity?
saying, yeah, that's a very good question. And yes, in the question when I'm asking, it doesn't matter. But when you are analyzing, you have to make sure which is coming
You
from
need
that.
to know the history.
Yes, in the analysis, yes.
A snapshot will not work.
No. But the thing is, when you ask the question, you are only asking about the snapshot. Yes, you have a question.
How is this kind of distribution?
I'll tell you. At this point, what I'm going to assume is I'm going to assume binary branching. Every particle splits into two. Later on, I'll tell you how to. No, there are various distributions that are popular, like geometric distribution, etc., which are popular because of various analytic reasons. Various reasons why. No.
You define two things. One is this position.
Yes.
That is the
Yes.
distance from this just earlier parent.
Right.
And another is the displacement from the origin.
Yes.
But finally, we will look on the long run,
Positions.
long run distribution of
The positions, yes. Because I'll see the snapshot, and there I'll forget about the displacement. I'll only see where they are. So I'll look at the long
And we
run.
will look only positive.
Yes. So this is in the simplified model. I'm only looking at positive displacement. Everything is moving towards right, just to make life easier. Any other question? Very happy there are so many questions. That's always a good sign. Okay, so let's move on. So now I have to make it a bit more precise, and as I said, I'm going to go on making things easier and easier. So I'll make two simplifying assumptions. One is that we'll assume that each particle branches into two particles. Always, there is no randomness in there. So the Progeny distribution is just always taking these two randomly with the value taking. Okay? So this is a simplification which I'll talk about how to get rid of that. Okay. So this is therefore will generate what is called the binary branching value. Binary coming from two.
That is with fixed order.
Always two.
Two P1. P1 minus P second Q1.
No. Not like that. It's just always breaking into two. So there is no P1 minus Q. There is no randomness.
Okay.
Otherwise, another case could have been either with P probability branches into two particles, or with 1 minus P probability branches into three particles. I'm not allowing such. I'm making life very easy. Always branching into two particles. Second, we'll also assume, as I said, we are assuming that the displacements are positive. The entire dynamics takes place in the right side of the real line. So it's positive. Also, I'm going to assume that all of them are independent. Of course, I have already told you in the model all the displacements are independent, but also I'm going to assume they're identically distributed in the sense that all of them have the same distribution. Making a lot of assumptions here. So that's in probability of statistics called IID, just means independent and identically distributed. So they all have the same, they're all coming from the same distribution, and I'm going to assume they have a power law distribution. And I forgot to write, it's a continuous distribution, I'll assume, just to make sure that they don't collide. They don't take the same space. They'll always be different.
So power law.
I'll tell you what power law means. So basically, that if you have displacement is d, that's the distribution. Displacement is going to be say bigger than x, for a big x will be some constant times x power minus alpha, where alpha is a parameter or tail parameter, which is between 0 and infinity. This is basically something positive. So what I'm saying is the following. So just to give you some context, I think I should unshare this so that I can use the board. Yeah, thank you. So just to give you some context, so what I am doing is this. So say you have a probability density function like this. So D has a probability density function. So this is 0, this is infinity. And then I'm looking at this. Okay, this is the probability density function of D. Probability density function of D. Probability density of D, which basically means the total area under this would be 1. Okay? Because total probability is 1. So this basically just means that probability of D is taking value between two numbers is just if this function is f, say f, and this is x here. This is just the integral from a to b of fx dx. That's all this means. Okay. So in particular, if I look at probability of D bigger than x, this is just integral from x to infinity of this. Okay. I should not have used x here. I should have used t. T is time, so let's use du. Okay. Sorry. Yeah. So fu du. Now this is what I am calling power law. So this will be like some constant times x power minus alpha as x goes to infinity. It means just for large x, it's like x power minus alpha up to a constant. Constant doesn't depend on x. And if you want to make it formal, what it means is that if you look at this probability, you divide by this guy and take x go to infinity, that goes to 1.
Is there any restriction on alpha?
Alpha is between 0 and infinity. So
That will allow for integrability.
I don't need anything. That's a good question. I don't need anything. For the questions I'm looking at, I don't need.
How are you making the area one?
Area 1 is always there because see, the point is, I'm not talking about this small function f. I'm talking about the bigger one. That's what. Yeah. As long as it goes to 0, it's fine. Okay.
So mean
Mean may not exist. Yes. That's what he was asking. Mean may not exist. I'm not going to talk about central limit theorem, etc. If I need to do that, I have to make further assumption on that. So yes, mean may not exist. So the kind of question I'm going to ask is about extreme values. Their mean is not so important. More interested in the extreme values, like the higher values. So mean may not exist. Okay. So now I'll go back to the slide sharing again. Thank you. Thank you so much. Okay. So thank you. By the way, again, I always use this phrase Levy flights, but I'm not an expert. Again, I might talk to you. You might know more about those. Yeah. But anyway, so I laid it in the lecture note that I was talking about. That in ecology they have these models that power law may arise naturally. So anyway, so apparently the predator prey network, when they analyze it, they observe power law. But I'm not an expert. Yeah. Okay. So I have this kind of power law, IID. So alpha is a parameter, of course. My answer will depend on alpha, whatever question I'm going to ask. I have not asked any question yet. I'll ask it. The question is, how does the system look like in the long run? Again, the question is vague. You have to make it more precise. Again, little bit more precise, but still vague, is how fast the system of particles grow as time goes to infinity. Time meaning, remember, time is discrete. Okay, that the f of goes to infinity. And what is the scaling limit? What is scaling limit? We'll talk about it. It basically means that if the system grows at a certain rate, you scale the entire system with that rate. Do we see some pattern? That's what scaling limit means. Okay, so here is the point. The very easy thing will tell you that at the nth time point there are 2 power n many particles. That is something even a high school kid will tell us. Mid school kid will tell us. Suppose at time 3 you have 8 particles. Okay, well, suppose you are at time 3, which means you have 8 particles. Now, one of the things that you can look at, I told you I'm an extremist person, so I'm interested in the extreme values. So, but I have values. So, yeah. So this is the rightmost point that I want to look at. Okay? So you have 8 particles. The rightmost point. How far is it from the origin? Okay? And that, of course, is a random variable because all these things, all the movements, the number of branching always is 2. Splitting is always into 2, but the movements are all random. So therefore, all of these points are actually random points. The rightmost point is also a random point. Question is, how does this Rn grow as it goes to? Now the story goes like this. When we first, my student and I, and then Rajat also was involved, we were working on this. We actually solved this problem. We were really, we're dancing. Yeah, we have solved something. And then on one afternoon, our milkman had come in our house, and at that moment, I realized that Yeah, I realized that this has been done 1980 whatever, 85 or 89 something. So I asked the milkman. I had asked the milkman just before that. Okay, please wait. I'm going to give you the the whole variable put the. This is a traditional milkman, and I totally forgot that. And milkman, even if he is not a mathematician, he also stood for some time. He should have rang the bell once more. But I realized I shouldn't be disturbed because I'm anyway disturbed. So he just went in. So this milkman story I always tell you because in research you should always search. That's very important. We didn't do that, and then we solved this. Then we were happy that we saw that this has already been done. But there are two good things out of it. One is that whatever we did matched with the theorem that was already proved by Lee Kuret and would refer to it. Secondly, that gave us motivation to do something more. So we thought, okay, rightmost is done. Let's do the second rightmost. At least let's improve it. So that was the idea. So then, question is how fast does it grow? Rick Durrett in 1983 actually, but in 79 there was one paper, both papers I guess, told that, okay, forget about this symbol, I'm not going to tell you what it means. Basically means that the system, if you look at this system in the nth time point and n is very large, it grows like 2 power n over r. And this alpha is the same parameter that is here. Okay. So this is the result that because of which the milkman had to wait and then went for some power amount of time we waited and then said, sorry for that. Okay. So then this basically means that if you look at the rightmost particle position, which is a random variable, you divide it by 2 power n over alpha, this converges in distribution to a strictly positive random. If it converges to 0, then I cannot say it grows exactly like 2 power n over alpha. So since it converges to a strictly positive random variable, and exactly we also know what is the distribution of the limit, etc. So basically, this is telling you Rn grows like 2 power n over alpha. It's also telling you the scaling limit of Rn is also known. Strictly positive random variable distribution. Okay. Now, as I said, since we already saw that it's already done, we had to do something new. We said, okay, let's look at second right. So we look at all of them. The second rightmost, you have 8 points here. This is the second rightmost. Of course, I have n equal to 3, but I want it for very large n. Question is, how fast does it grow as n goes to infinity? And again, is there a scaling limit? Another important statistic was the gap statistic. Namely, you look at the rightmost point, and then you look at the second rightmost point. You look at their difference. That's the first gap statistic. And gap statistics are important in statistical physics. We didn't know that. My student was giving a talk in Poland. I think it was in Krakow, and Gregory Sayer was there, and he asked this question. Then we thought, okay, we'll use also our tool to solve that. So we solved that as well in the same paper actually. Sure, sure.
Since these are independent, or I may be wrong, you expect Poissonian kind of.
Yes, thank you. Very good. I always good to have smart audience like you. Thank you. You have a Poissonian. But the Poissonian is not direct. There are some other things. Some dependents are there. But Poissonian, very good. Thank you.
Like rightmost one,
Yes.
can have a similar definition, but the leftmost one as well.
Yes, you can. You can. Here, the thing is, rightmost is more interesting because we are the main dynamics happening towards right. So if I allow both sides, then of course, leftmost part we can also. Similar analysis can be done. You can.
No, I am talking about your model where.
Yes, we can. We can. Here also we
to
can.
the right.
Yeah, left also.
Then there should
Yes.
be a leftmost.
Yes, yes, we can do that. Yeah. Yeah. Because what we are going to actually we did is the entire point process from there, everything.
And leftmost and rightmost have the same behavior.
No. In this particular case, when things are going towards right, then you don't have the same. If you have symmetry, then yes. Or some kind of symmetry in the distribution of the left side and right side, then yes. Some qualitative similarity is there, then they will have qualitative.
Both of leftmost should be much slower.
Yes, of course, as you can expect. Because rightmost one is moving faster. There's a speed. Yes. Yes. Yes.
Let's say for what at one step,
Yes.
what will be the
One step meaning.
means that first step is equal to 1.
Or
What will be the other rightmost?
you have two particles.
Yes.
Whichever is on the right part.
So now this is random distribution 0 to infinity.
Yes. Yes.
So then
You can compute it explicitly if you want, but yeah, possible. It's just Basically, you have two, very easy, you have two independent random variables, you know the distribution of each of them. You just have to, yeah, you just have to find out how to.
But the distribution is given.
Distribution is, well, distribution is not totally given, it's just asymptotics of the distribution.
Here.
From that, you have to find. Yes, so basically it's a bit more universal than a particular distribution.
So this is like the expected right position of the rightmost part.
I would say expected, I would say the distribution. Expected means mean may not exist. But what I mean, what I want to say is that I have a habit of making puns, but that sometimes goes against. So yeah. So what I wanted to say is that here I want the distribution. Like, what kind of distribution? Like he said, Parthanil. That kind. Does it follow some known distribution, or if not, what kind of distribution? In other words, if you look at say the second rightmost point, to scale it appropriately, it will converge to say some positive random variable. Can you find this probability density function? This kind, very explicit.
I see.
Yes,
But
sir.
can you go back to the previous slide?
Sure.
Rn.
Yes.
So here you are saying this Rn is, it goes like this. So you want to give a probability distribution for the.
Yes, I can tell you what the distribution is. I can write it down.
That
I
I'm
didn't
not
want to write it
understanding.
down because I was not needing it, but I can write it down. Go ahead. So, okay. So, since you asked, it's a good question. So, let me answer that. So, the rightmost point was Rn, right? And I told you that the probability that Rn over 2 power n over alpha, this is say less than or equal to x. You take some x positive, fix an x positive. You look at this probability. As n goes to infinity, this will converge to e power, this is called Frechet type extreme value distribution, e power x power minus alpha. This is the same alpha as in the parameter. So this is a probability distribution function. So this is called Frechet type. Frechet type. I always forget, and French people hate me for that. Whether it's this e or that e, anyway. Frechet type extreme value distribution. Extreme value distribution. Okay. So this is a very explicit distribution. Now, same question can be asked for the second right, third right. So now it's clear.
Yeah, nice.
Thank you. Anything else before we move to the?
Also, I mean, one important question is what is the radius of the blob or the extent of the blob? That will be probably
Right,
of
the range.
size of
You mean the range? Yes, that's another question. Yes.
But that should be probably of the size of the rightmost.
Yes, of that order. Because the slow, as he said, the slow growth of the leftmost will vary that.
And also
Right.
the density.
Yes, I think so. I've not done it, but my intuition says that because of that, at that scaling, when you do that scaling, the leftmost will go away. Wash away. Yes.
The distribution of the second leftmost is the same or different from this system?
No, different in this model. Different because left side is growing a bit slower as one other one.
Second rightmost.
Second rightmost. Yeah, the distribution is going to be different, but you have a very good point. The growth would be the same. Distribution would be different than this, but growth would be the same.
It will try to avoid the first one. Right?
Yes, so that will be seen in the distribution function. Yes.
Some sort of repulsion.
Yes. Because of the heavy tail nature of the part. Very good. We should talk more.
No,
No, seriously.
This is intuition.
No, that's it. That's what okay, by the way, I should tell this. This is not a joke. This is serious. Okay? So I have read this somewhere. Is that Harish Chandra, arguably at least one of the best mathematicians from India, was working with Paul Dirac, and then once he asked, he had a very basic doubt about himself, and he asked, "Should I be a mathematician or a physicist?" And Dirac was very clear. He said, "Given your nature, I think you should be a mathematician because it's much harder to get." And I think he meant it, and I believe it because I think it's you guys have much better intuition than me. I just can prove some theorems. That's all I can do. But intuition many times comes from the physicists. Like Deepak, for example, is one example. Another here is another example. But anyway, I don't want to mention names like that. But there are many such people. Yeah. Don't worry. And he said unlimited time. Okay, so how fast does the second one grow? Graph statistics, etc. Now, the thing is, intuition is the following: the entire system is growing at the rate of 2 power n over alpha, and therefore order and gap statistics, which means second, third, etc. And all the, by the way, this is the second gap statistics. All of them are growing the same rate. And the question is, how do you find limits of those? And that's what I'm going to tell you. There is some bit of calculation will be there, but at least I'll, you know the context. So, one, of course, you can use brute force method. You can use different techniques to find out, first rightmost, second rightmost, third rightmost, but that's not going to be efficient. Another method is neither elegant nor efficient. Another method is what is called point process technique. I'm going to tell you a glimpse of this today. You can think of this as a master key for all the logs. All the questions that can be asked, well, a lot of them at least, can be answered using method 2. If you are lucky. In this case, we were lucky. So I'm not going to present the full generality of this method because it needs a lot of technicalities. And there is a carpet here, I'll use it. I'll hide everything under the carpet. I'll only talk about very briefly a glimpse of the whole thing. So because Manada said I maybe I'll be a little bit faster. So I'll use this thing, don't worry too much about it. I'll use something called convergence in distribution. Don't forget about this technicality. I'll just think of it the random way will converge into random way in distribution. That's sort of understood. Okay. So what is the master key? At least let me tell you what is the master key and then how to find it, etc. I'm not going to talk. So here is the master key. So you have the entire system is growing like 2 power n over alpha. So what we do is we look at, say we take an x, we fix an x positive. Earlier also we had fixed an x positive here, right? Do that. Entire system is growing like 2 power n over alpha. So what you do is you blow x up to 2 power n over alpha times x. This is same as shrinking down the entire system, but shrinking makes it difficult to look. Where you're going to use a microscope and the entire thing I'm going to make 2 power n over alpha times x. So I'm magnifying the x. Okay? I'm magnifying the x, and then this is this point start after magnification. And I'm going to look at how many of my, say this is n equal to 3, there are 8 particles. How many of my particles are to the right of this star, the magnified x? So this number of particles at time n which are further away than magnified x away from 1. Okay, in this case it's 5. And in each of these, if x is a fixed number, each of these is a discrete random variable, and they take values in the set 0, 1 up to 2 power n, because at nth generation there are only n 2 power n many points. So my minimum is 0, maximum is 2 power n. That's it. There is no other possibility. Of course, in the limit, it will be all possible non-negative integers. So in the limit, of course, because 2 power n is going to infinity, so it will be that case. Question is, for each fixed x, can we find the limit? Forget about what is weak limit. Can we find the limit of these guys as n goes to? This is what I call the master key. I will say, why is it the master key? I'll tell you that. I'm not going to tell you how to solve this. I'm just going to write down a theorem in the end. I'm going to tell you how to use this theorem. If at all we find this limit, how is it going to help us? That's what I'm going to show you. Is that clear what I'm doing? I'm magnifying I have an x, I'm magnifying it, thinking that the entire system is going that way. So let me magnify x. This is same as entire system shrinking by 2 power n over alpha. I'm instead of making it shorter, I'm smaller, I'm making it x bigger so that things are at the right scale. And then seeing how many points are there to the right. Sorry. I saw. Okay.
Audience are in here.
Now suddenly. Maybe the battery. No, you can carry on. Online. Is there anyone online? Okay, I'll carry. Okay, so in the interest of time, I'll carry on. But yeah. So this is, as I said, this is the number of particles to the right of this, and I want to find. Suppose I'm lucky and I found the limit. So remember, my x is fixed. I'm not taking x to infinity. I'm only taking n to infinity. N and x, remember, is the number of particles at time n further than magnified x. So I'm looking x under a microscope. It's magnified to 2 power n over alpha x. Further than this away, I want to suppose I have found the limit. How does it help me? Suppose I have found the limit. Now I want to find, say, whatever Rick Durrett did in his theorem. Meaning, I'm going to look at this result here. I'm looking at that. So that means the rightmost particle is less than or equal to 2 power n over alpha times x, which means to the right of the 2 power n over alpha times x, there is no particle at all. Right? When is the rightmost particle less than or equal to this magnified x? If and only if nx is 0. So now I know that this is the limit. The limit would be just instead of n you put infinity. I've told you nnx goes to n infinity x for every fixed x. So I know this. So from here I'll be able to recover this result. If I know the exact distribution of this guy, in particular I just know this probability, I'll be able to recover Rick Durrett's theorem. Now I would say, oh, you recovered Rick Durrett's theorem, big deal. It was done in the 80s. Now I'll tell you something not done in the 80s. Look at this guy. Suppose now you look at, again you assume that this limit is there. Now look at the second rightmost particle. Now I have told you intuition wise this is growing at the same rate, but possibly different distribution. We are going to just look at this. Same thing. Now, under what condition will the second rightmost particle be less than or equal to magnified x? There are two possibilities. Either all the particles are to the left of it, there is no particle to the right of this magnified x, or there is exactly one particle to the right of it. So nnx can be either 0 or 1. These are the only two possibilities. There is nothing else possible. So this probability here that I am after is just the sum of these two probabilities because these two are disjoint also. And each of them has a limit because of the assumption. So I told you the limit is explicit enough to compute these guys. Using that, you will be able to recover the second rightmost particles asymptotes. Of course, I have not told you the limit. I'll show you the limit very towards the last 5 minutes. So this is how it looks like. But don't worry about it if you don't find the limit very helpful or very friendly. It looks a bit odd because of various things. But remember the principle that this method will help you because of the explicit nature of the distribution of n infinity x. You'll be able to recover not only Rick Durrett's theorem, but also the asymptotics of the second rightmost particle, third rightmost particles, gap statistics, etc. I've just shown you how to do the second rightmost. Other things can be done as well. It's working now. Okay. So in the same notation, now I just want to tell you how this limit looks like. The limit looks like, very simplistic terms, some 2 power gi's summed up to some 1 to px. Okay. Now what are these gi's? What are these px's? I have to tell you. So gi's are what is called geometric distribution. I'm going to tell you what that means in the next slide. Otherwise, I'll write it. So you have these are geometric distributions with parameter half. N union 0 is just non-negative integer value, and px is a Poisson, as you know, this clever gentleman already guessed. You know, if this is a Poisson random variable. There is Poissonian here, but there is more to it. There is Poisson coming in because of the independence of the particles, but there is more to it. The geometric development. And all of these random variables, px and gi's, they're all independent. Okay. So you have, so forget about if you don't follow what it is exactly. The point is, it's very, 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 very explicit. In the sense, from here I'll be able to compute what is the probability that this is equal to 0. What is the probability of this guy is equal to 1. What is the probability that this guy is equal to 10 and so on. Interestingly, because it's the sum of 2 power things, partition, how can you partition a number 10 into sum of powers of 2 comes into the picture beautifully in these computations. But I'm not going to go into the details. But here is a bit more explicit how the limit looks like. These are geometric random variables. So these are basically means these are random variables which are taking values in the non-negative integers. And probability that it takes a non-negative integer value is 1 over 2 power m plus 1. Forget about all this mathematics. It's just this random variable. Suppose you have unbiased or a fair coin. You toss it, okay, you keep on tossing it. Number of tails you will get before your first head has this distribution. What I said, so you're tossing a fair coin independently over and over again till you get your first head. The coin is fair, so it has probability half. Number of tails you get before the first head has this distribution. So what is the chance that you will get head immediately? No tail before the first head. What is the chance? Half, right? So that's m equal to 0 here. That's half. What is the chance that you will get exactly one tail before the head? Tail followed by head. What is the probability? Half into half. That's 1/4. Then tail head is 3 and so on. 2. 2 head tails followed by a head. That's 2. And this one is a Poisson distribution. I think many of you are familiar with it. The only thing is the parameter of the Poisson has a parameter of the system in it. X power minus half. This x is the x which you are magnifying and looking how many points are there right now. So all these random variables are independent, and therefore in particular you can compute all of these probabilities. You can compute all of these probabilities and so on. So basically this means, okay, by the way, this just means whenever px is 0, this is 0 also. If the Poisson is taking value 1, then this is just 2 power g1. One geometric is going to be used. If Poisson takes the value 2, this is sum of 2 power of 2 geometrics and so on. So you can, so in other words, if you want to simulate the limit, it's very easy. First simulate the Poisson. If the Poisson takes the value 10, you simulate 10 many, it's a sequential process. 10 independent geometrics, 2 power them, sum them. That's how you can simulate this. Okay, fine. So you can do many computational things using this simulation. Okay, so any question? Because I think I'm going to more or less stop here. I have some remarks, but those are not so important. Questions is more interesting.
Power law is very difficult. So that when one tries the Gaussian distribution.
Gaussian people have looked at, it's done.
With a,
Yeah, it's done. So there people have looked at all these things. They have looked at yeah, this is a huge body of paper. And by the way, I should have told you that the fact that I'm telling you all these limits exist, this was already predicted by 2 smart physicists, Eric Brunet and Bernard Derrida, and they had predicted something called what they call decorated Poisson process. So Poisson was already there, and what we got is again decorated. We call it scale decorated. So they predicted in the Gaussian case. In the Gaussian case, they get decorated Poisson process. Once you have power law, you have very big values. So then you have to do what is called scale decorated. There's something else, but that connection is there. You can go from one to the other. But proofs you cannot do. The dynamics is very different. The reason is here, very simplistic now. This is called one large jump principle for power law. This comes from finance. Suppose you have an insurance company and you are looking at claims. You have some capital to start with. Claims can ruin you because if you have a capital of this much and you have, of course, if your insurance company is not a charity, so you are taking the premiums, but total amount that you have, initial capital and premium, if one claim crosses it, or maybe some of many claims crosses it, then you are done. Right? You're ruined. Now it so happens that if it is observed that the claim sizes typically follow a power law for various reasons, and then one big claim can completely ruin the system. And this was seen many times. For example, if you have followed news recently, there was some banking crisis. There also, because of some more big claims, not claims, but some loan default in that case, one big loan default can completely collapse the system. That's why I think bank system can be very, very, very unstable, even though we think it is. In fact, I got an email at that time from some hedge fund saying that you see, bank is so unpredictable, so don't put your money in banks. Please invest it in the mutual fund instead. So I thought it's a joke, really good joke to share.
okay.
Yeah. So anyway, so
Maybe I can ask you.
the dynamics is very different. Yeah. Yes.
So this Gaussian what you're talking about. So Gaussian is like a distribution of the inherent length scale.
Yes.
So this power law doesn't have that.
That is a very different length scale. Yes. And also, a lot of small contributions of displacement will contribute to the extreme. Here one big contribution will make.
So there is proof of this
No,
point.
we don't
Because
know.
I can see a hint of kind of RG kind of
No.
argument going
Yes,
there.
yes, yes,
Scaling the
yes,
system,
yes.
that those
Exactly,
things won't
exactly. So it started working suddenly. Yeah. So yes, it's not going to work. Yeah, I mean that this is a completely different world. In fact, in the Gaussian, I think the state of the art is that whatever I call the point process or whatever that scale thing, how many are there, etc. People know that there is a limit. People know that the limit satisfies certain symmetry in the limit. It's called superposability, and hence, because superposable processes have a particular form, Poissonian form, they know it's Poissonian, but they don't know explicitly how it looks like, as far as I remember. So it's a very delicate proof where they use the superposability of the limit, because we know in physics, I mean, things may not have the symmetry, but in limit there is symmetry arises because of the limit. So in the long term limit, so that happens here as well. That also superposable. Okay, so these are some exercise problems. If you want to try, I'll share the slides by the way. Show that the second rightmost exactly looks like this. So this is explicit. So this answers one of the questions with a different distribution. Okay, and so you can see that the second rightmost is away from the first rightmost by this amount. You can see the explicit of this amount. So in general, you can talk about third rightmost. There are more exercises. Don't have to do that. I'm just telling you. So for example, partition of K becomes important. This I'll skip. I'll just tell you the heuristics. I'll just skip because there is not much time. I'll just tell you the remarks, final remarks. One is that instead of m, if I have m, I have m offsprings, then instead of 2 power gi in the limit, I'll have m power gi. If branching happens according to what is called a supercritical Dalton-Watson process with finite mean mu, then so it just means that you have each of them will have independent, identically distributed number of particles as their offspring. That number should have finite expectation, number of particles born in the next generation, and the expectation should be bigger than 1. That's called supercritical. Then, if the expectation is mu, progeny mean, that's called the progeny mean. That's the average number of children. Progeny means the average number of children. So if progeny mean is mu, then 2 power gi will be replaced by mu power gi. That's the only change. And then we have also investigated answering a question of the say that gap statistics. So we have verified the conjecture of Brune and Derrida in our setup, and then we have been able to link this the paper of Derrida, Molchanov, and Zurb. This paper had nothing to do with physical physics or branching random. This was considering stability of a system, and then stability refers to something else. It so happens that the superposability that was there in the Gaussian case, in the conjecture of Brune and Derrida, if you change it correctly, it becomes exactly the stability of these guys we discovered, Derrida, Molchanov. And of course, we have extended this to dependent setup. Basically, the offsprings from the same parent can be dependent. Multi-type case, branching with infinite progeny, various other things. I don't want to go into that. I guess there are various open problems that one can look at. This interaction is one thing, like either annihilation or coalescence, and then statistical inference. Like say, for example, in this setup, suppose you observe the nth generation, and then how to estimate alpha. That's a very difficult problem. We tried it, we couldn't do it. But if you, I think it is possible if you don't observe just the n, if you observe and if you know the genealogy of last few generations, it's possible. Then we are to think.
But nobody bothers to know the density profile.
Well, simulations there are. I don't have the pictures yet, but we haven't been able to prove any result. Hard.
A very somewhat similar problem is single file diffusion problem in physics. I don't know how to say that. There people are very much interested in density profile and similar questions like the rightmost
are arising there.
Yes. Next to rightmost.
Yes. Also, there is something called I'm only talking about discrete. The continuous version is called branching Brownian motion. Let's not describe it, but there also this kind of this density profile question answer there. People only know the rightmost, etc., but people don't know that. That's a very difficult branching problem.
That can be guessed probably. Right?
There are guesses. There are guesses. No, there are many guesses. No, there are many guesses because people have done simulations, etc. But formal proof are not there. Any formal proof would be this. For example, this one, this itself, Madhur just showed the existence of these limits. And he showed that the limit satisfies superposability and hence it has to be decorated post solving. So there was another paper of Pascal Maya that proved that. But then we don't know the explicit limit. That would be another question that you are asking. And then various other things.
You said annihilation, but particle death, I'm guessing particle death.
Yes, that when two particles collide, they die.
Just by itself.
Oh, just by itself. That's another thing. Yes, particles suddenly it dies.
Still
Yes.
non-interactive.
Yes, yes, yeah. Just like that, the particle decides to die.
Then
Like
I'm
Veronica.
guessing that this will arrest. Okay, sorry.
Yes. No, go ahead.
So this will arrest this growth, I guess. You have sufficient particles.
Yes, of course. If you have sufficient, there might be a competition.
Right.
That would be.
So
what is
what I'm
the
driving at is that will there be a phase transition?
And that would be a very interesting question. I don't know the answer. My guess is yes. My guess is yes, because if you think of it, if particle dies with probability close to 0, then we are back in the same system.
Right.
And if dies with probability 1, then we are all gone.
Because
So it has to be a phase transition.
reason I'm asking is because we please understand phase transition with symmetry changes.
Right.
I don't see the symmetry.
I don't know that also.
So that's
yeah.
why I
Now, if RG can be done, we haven't solved this using RG.
No, I know,
But
but
if RG can be
like-
done, yeah, RG like, but if RG can be done properly, I would be very much interested if RG can be done. So then that would be interesting.
see, I don't just see this. Usually when I think of phase transition, I think of what symmetries are
Right.
separating the two.
Right.
So in these two cases, I can see those.
Because here there is no phase transition as such yet.
No, but suppose you bring in say.
Yeah, if you bring in, then that would be interesting. Yeah, we have to see. Yeah. But the idea, my guess is that there will be at least one phase transition for sure.
Yeah, but then
Might be multiple.
what symmetry changes?
I don't know.
can
I
see
don't know.
that.
We have to think about it. Yeah, exactly. Any other question? I think I am done. These are the papers, and we actually presented the last one mostly. Well, the first one. Chronologically, that's the first one. And these are all. Sure.
Delta function distribution or the number of proteins?
Yes.
Two, or
Fixed one. Yes. Delta function
But
distribution.
when
Yes.
you allow this,
Yes, that's what she does.
so that is when it is when it is actually a distribution.
Yes.
Not
Yes.
just a
Yes.
distribution. Then many of these geometric things that you are saying, some 1/2 to the n plus 1. or
Yeah, that
these things will not work.
No, it arises. See, if you don't allow sudden deaths like that, if you just allow, say, random number of particles born, and there you allow 0 also, 0 particle bond is also allowed. If you only allow death during the branching, not in between, then you can still solve it. Because then you have to replace 2 power gi by mu power gi, where mu is the progeny
We use the mean.
means, if that is bigger than 1. But the question is, what she is asking is, the particle decides to die suddenly, and then it's much harder. And I'm sure there is a phase transition. Absolutely sure.
Here, why is mu greater than 1?
Oh, that's because it's just very easy. This supercritical branching process, on the average, if you have less than 1 next generation, then it's going to
Die.
blow up. It's going to go, decay, to go to 0. On the average, if you have 1, then also it actually goes to 0, can be shown. But if it has more than 1, then only the system will grow. And we want the system to grow, right? So
We are
that's
saying this is interesting, yes, but I think this will still hold, right? This what formula I have derived, that will still hold, right? Even
which
if it
mu is less than 1.
Yeah.
No, the question won't make sense because the system is going to go off to 0. So your rightmost particle will
not
become
well
something
defined.
trivial. Yeah, the question can make sense, but it may not have the interesting limit. It just stop somewhere.
So, mu equal to 1 probably in the sense of phase transition is critical.
Critical, yeah, but there also I think
Are there any results?
some people have looked at it, but I don't know whether it's a heavy case. I have to look at it. Mu equal to 1 might be interesting. You're right.
I mean, so what is the limit?
Right, what is the limit here? Mu equal to 1 might be interesting. You have to do mu equal to 1. The main problem is the following. The problem is I was hiding a lot of things under the carpet. Entire thing you do under the whole analysis is conditioned on the fact that the branching process survives. Now that has positive probability under mu bigger than 1. If mu is 1 or less than 1, that has probability 0. So conditioning will go away. You have to make the people still condition under 0 probability events, but that has to be first made sense out. Maybe you have to do it at nth generation and then take a limit of under conditioning. But that's a very good question. How to formalize it is also think we have to think. Especially with the v equal to 1 case, might have an interesting limit, but we have to think of it. Whatever we are doing is not going to work, but that doesn't mean it don't going to work. It's going to work after some twist. We have to think about it.
What will your last slide, please?
Yes, please. Last one in this one. Yeah. Oh, I can email you. Yes.
So why the rates for each extremes is same?
That's a very good question. Yeah, this is again because of the one large jump principle. Because what happens is all of them, all of these guys, first maximum, second maximum, third maximum, etc. If you only consider this kind of things, then all of them are basically influenced by one big jump, like one particle making a big displacement somewhere.
Being the rightmost part.
Rightmost, second rightmost, all of them influenced by the same guy in the limit. That is why all of them are the same group. But of course, they distinguish also because of the limits are not the same. The distinction happens at the limit, but growth is the same. It's a very good question. It happens because of the power law.
And why the leftmost particle doesn't follow the same growth rate?
So here I have an asymmetry in the system, right?
No,
Because
I mean,
now if you allow symmetry, then yes. In this case, what
time-
happens if you simulate, you will see that some particle will come to the left near 0, etc., etc. So very slowly go towards 0.
Right, that is true.
But rightmost it has a lot of space to grow.
Right.
That the topology of left side is not same as the topology of the right side.
No, I mean, if you just consider the difference. I mean, if the
Then you
first-
they have to
first and
scale it,
second-
etc. You have to.
No, if the first and second nearest, I mean, the
Yeah.
rightmost part, they
Yeah.
have the same growth, and the third and fourth. Can we? I mean,
Yeah, I haven't thought about that.
Can I represent this to be the density of your
Yeah.
zero grow exponential function?
I don't know that. Good question. We never thought about it because honestly we didn't even look at this particular model. We looked at both sided model with balanced L condition, etc. So their left and right qualitatively are the same. But yeah, this question is very interesting. I can think about it.
And also, I'm going to instantly limit this argument in a code, like most and second,
Yeah.
then a second and third and comes back to 0. We want to implement it.
So, but under time scale has to be changed or something.
Yeah.
Some change has to be made.
First taking n going to infinity.
Right. Possibly, you're right. I haven't, honestly, I have not given thought on it. I have to think. Very slow. Think.
I mean, asking you what the density in a particular case. I mean,
I have to
guess
do that also. We have somehow
Will it be like 1 by g gap, right?
Something like that.
One particle per gap. So, since it's exponentially decaying e to the power minus x alpha, so it has to be very fast decaying.
Right. Towards the
Very
right
fast
side,
decaying.
yes. Towards the side.
I mean, yeah, the origin I think is finite growth, not.
No, it's growing like no. This is if you look at the bigger than x, if you look at bigger than x, right hand side, right? That's not exponential. This is converging. Sorry, bigger than x. This is converging to 1 minus e power minus x power minus alpha, right? This as s goes to infinity actually behaves like x power minus alpha. As s goes to it's powered because 1 minus e power minus u is like u, right? As u goes to 0. When u is u goes to 0.
Density will be a derivative of these.
Yeah, density will be derivative of that, but the point is,
I mean, just
yeah, that I don't.
the derivative right now.
No.
It's strictly power. I see.
Oh, acha.
So I mean, it is 1 by
If you
x.
take the-
Oh, you
alpha
mean
less than
no,
one
no,
or greater
we
than
are
one
talking about this one only.
No, I mean,
So alpha greater and less than 1 will be different. You take the derivative.
Yes.
When you take the derivative, alpha
Right.
greater and less than 1 will be different.
Right.
When alpha is less than 1, you will have finite value.
No, so that depends on alpha.
Yes,
I mean,
yes,
right,
right.
it depends. Oh, I see. So this is exponential density of
Yes.
exponential.
Exactly.
So alpha greater than 1.
Any other questions?
Very good. So many questions.
Related to this question.
Yeah.
So, suppose that you have the same branching process, and suppose that you take a slice in between somewhere. Now, if you ask the question, that what is the particle density on the left side and the right side? Will that be any change there? How particles are moving some barrier or moving from this side to this side?
Yeah, my guess is that the barrier depends on n, right? Because unless the barrier depends on n, because particles are anyway moving towards right.
Yes, yes.
Fix your barrier is doesn't not depending on n, then eventually you will see more particles towards the right. That's- yeah.
It depends on the position of the barrier.
Yeah, if the barrier depends on n and it moves, then it's different. Almost probably to make sense of your question, you may have to may have a barrier which is moving also with n.
Okay,
Then it
because
might be.
the distribution is power law. So somehow always some particle will be there where not actually not moving. So,
So your barrier remains fixed throughout n, right?
uh,
In my case, is that more particle will
left become hacket after some
more or
time.
less. I think so. Right. After some time, all particles will start going. That is my case. I have to check. I have to see do the simulation and check.
So if the movement is symmetric, then how the result will change? That is the limit.
Oh, if the symmetry is there, it don't change much. Thus, yeah.
Still 2 to the power n by alpha.
Yeah, 2 to the n by alpha. The only change will happen in the rightmost point. Nothing will change. In the limiting point process, some change happens, but yeah, not much.
So yeah,
Qualitative
qualitative
will
will change. Another thing is that recently there are a lot of works on this log potential and the
Right.
distribution of rightmost same question.
Right. Log correlated field.
Yeah, right.
Yes, and they're related. They're related. In fact,
How do you compare the results?
so I don't. Okay. So in the log correlated fields, in many cases, like Gaussian field, etc., people have observed limits which are again recorded for some cases. So, and in many cases, they have actually what they have done is they have compared it with some branching random walk and solved using branching random walk. But see, again, these are all light tail cases. So that is why things are, I told you things are related, right? There was one paper where they looked at, I think, Gaussian field. They have log correlated behavior. And there the limit of the maxima is related to the limit of the branching. Zanshi's book will have these things.
Are you aware of the
Recent ones I don't know so much.
Mohinder and Ghosh and so they log potential. I mean,
They looked at log potential. No, I have to look at it.
some exist results.
Satya will.
Okay, are there any questions?
Election, send me those.
Okay. Okay, if not so, let us thank the speaker again. So, can you say that it is a benefit?
This is